Before we take our deep dive into all the ins and outs of alcohols and amines in substitution and elimination reactions and achieve all these fun goals, let's just review what we already know about alcohols in substitution and elimination reactions. So you should pause now and analyze these two reactions. You should know the mechanisms. All right, so we have an alcohol, tertiary alcohol, in fact, treated with sulfuric acid, a strong acid. This undergoes an E1 elimination to form an alkene. So we have eliminated water. So the hydroxyl and the beta hydrogen to make the alkene. Now the second reaction, we have a tertiary alcohol treated with HX. So one of our group 7A acids, halo acids. And we have the H part. This is going to turn hydroxyl into water, make it a good leaving group. And then the X part, the halide, does the substitution. And this proceeds by an SN1 reaction. So now that we have briefly reviewed, if you didn't pause before, you should pause now and provide the mechanism for this reaction and include the types of each elementary steps and the HOMOs and LUMOs involved. All right, last chance. Because this is review, I am going to go quickly through this first part, but you can certainly go look at the substitution and elimination, so the SN1 and E1 lecture, to get a slower, more in-depth look. So in general, when you see sulfuric acid or any strong acid, you need to protonate something, and it's no different here. So we protonate the alcohol with sulfuric acid to generate water. And now water is a good leaving group. So this bond cleaves, and it goes heterolysis, and we form this tertiary carbocation. Tertiary carbocations are electron-poor species, and what we see happening here when we treat with sulfuric acid is we just see an elimination because there's really no nucleophiles around. The conjugate base of sulfuric acid certainly is not reactive. It is a very weak base. It's a very weak base, and it's not going to react here. So I'm using water to deprotonate. Water is the strongest base that we have. So that undergoes an electrophilic elimination to give us the alkene product. Again, if you did not go ahead and try to review the substitution mechanism here, pause and do so. Now the difference between this reaction and the previous one is that we have HX, we don't have sulfuric acid. And X minus is going to be a nucleophile later, whereas the conjugate base of sulfuric acid, this was not a nucleophile. It's just not nucleophilic. Under some circumstances, it can act as a nucleophile, but commonly it does not. When we have HX, we generate chloride, which will act as a nucleophile later. So let's get back to it. So HCl is a strong acid, but we are going to protonate something. And what we protonate is the alcohol. So we protonate the alcohol, that generates water, which is delicious and also a good leaving group. So we have heterolysis occurring here to generate this tertiary carbocation. Now the tertiary carbocation is stable for a carbocation. It is still high energy. It is electron poor. We have the electron-rich chloride reacting in a coordination step to form the tertiary alkyl chloride. All right, your turn. So here's a slightly different looking substrate. So I'll have you go ahead and try to propose a mechanism for this reaction. Spoiler alert, it is the same sequence of steps. You just need to change the structure of the reactant. All right, again, we have a strong acid. We're going to protonate something, and we protonate the alcohol to generate water, which is a good leaving group. Protonated alcohol, it's nothing, you would never propose it as a product, right? It has a pKa of -2, and it's reactive, it's electron poor. So it's going to react, and it undergoes this heterolysis step where the water leaves. We get a tertiary carbocation, which again, carbocations are high energy, they're electron poor, but this particular carbocation is tertiary, and so it's relatively stable for a carbocation. We see chloride, the electron-rich species here, trapping the carbocation in a coordination step to get the tertiary product. And then at this point, hopefully you've noticed tertiary alcohol leads to tertiary alkyl chloride. So these are substitution and these are SN1 and E1 reactions, and they require a stable carbocation, right? And we know that tertiary is more stable than secondary, is more stable than primary, etc. And also delocalization of charge is good. So if you have resonance, that would be good as well. The rate law for an SN1 or E1, it's the same. It's just the rate constant times the concentration of the alkyl halide. So when we want to think about the rate, we want to look at the substitution of the alpha carbon. Is it tertiary? Or will the carbocation be resonance stabilized? And then you also want to make sure that X is a good leaving group. So is it going to be a stable conjugate base? Those are the two factors that affect the rate of the SN1 and E1, two major factors. Okay, we're going to do it again, friends. So consider treating the same tertiary alcohol, this time with phosphoric acid. Okay, we know that phosphoric acid behaves like sulfuric acid, not in the sense of their acid strength. Phosphoric acid is a weak acid and sulfuric acid is a strong acid, but they both facilitate E1 reactions of alcohols. Now, one thing is tricky. We have two types of beta carbons. We have this beta carbon that I have indicated in yellow, because these two methyl groups, they're equivalent. And then I have this beta carbon that I've indicated in pink. So we have two beta carbons, and they would lead to two products. If we eliminate hydrogen at the yellow carbon, we get a di-substituted alkene. If we eliminate hydrogen at the pink beta carbon, beta prime, we would get the tri-substituted, right? So we would make water a good leaving group. It leaves. We're going to get this carbocation. So we're really asking, where do we deprotonate? Well, you're right. We would deprotonate at the pink carbon because tri-substituted alkenes are more stable than di-substituted. Okay, so this is the product that we observe to see or expect to observe. But let's go ahead and draw out the mechanism. So you can pause and try. And it's going to look like this. So it's the same deal, right? Our first step, we have an acid, we protonate something. We'll protonate the hydroxyl to turn it into a good leaving group. That undergoes a heterolysis reaction to generate the tertiary carbocation, which is an electron-poor species. There really is not a nucleophile around, so we have elimination. So this time we can use the conjugate base of phosphate. Since phosphoric acid is a weak acid, we can use this conjugate base to deprotonate. And that will generate the tri-substituted alkene product. Okay, last one. So predict the product of this reaction. Well, sulfuric acid is a strong acid. We also know that its conjugate base is weak and not nucleophilic, and so typically it facilitates E1 eliminations of alcohols. So for this alcohol, I've looked at the beta carbons. It has two beta carbons, but this one doesn't have any hydrogens. So there's really only one possibility, right? This is the product, yeah? Elimination of the only beta carbon at the only beta carbon that exists. What do you think? Yeah, you're not going to fall for this trick. So actually, what we observe is this alkene, the tetrasubstituted alkene. And you can see, don't look at the mechanism yet if you are, if this is surprising to you, let me walk you through it. So you can see that we've definitely had some sort of skeletal rearrangement the carbons have moved around. The methyl, it was 3,3-dimethyl. One of those methyls has moved over. All right, why did that happen? Well, it happens because the carbocation rearrangement has occurred. Carbocations are high energy, and we try to avoid them when possible, and we'll get to that in just a sec. So same mechanism as before, we protonate the alcohol with sulfuric acid to generate a good leaving group. Water leaves. We have a secondary carbocation here. The secondary carbocations, they are less stable than tertiary carbocations. We could draw a little energy diagram up here for fun. Here's tertiary. Oh, yeah, that's a lie, right? Okay, tertiary is lower energy. Here's tertiary. Here will be secondary. So what we see happen is that secondary carbocation rearranges if it can make a more stable one. So in this case, we have a methyl shift where those sigma CC electrons are donated to the p orbital on carbon. That generates a tertiary carbocation, which is more stable than the secondary carbocation. Now, at that point, we have a more stable carbocation, but our only choice is to eliminate. So we have water eliminating the beta hydrogen, generating this tetrasubstituted alkene that is observed. So this is simply to remind us that carbocations can range. And later I'm going to say we should avoid carbocations when possible, because, they do funky things. They want to get, I hate to personify them, but I just did. They react to get to lower energy. So for example, if you make a secondary carbocation, it can rearrange quickly to make a tertiary one. It will, to get lower energy. We've seen a slide pretty similar to this before, not this exact slide. Again, I'm going to go over this pretty quickly. These three examples show three patterns in rearrangement that you will observe. So you should go ahead and pause, provide complete curved error mechanisms that explain the formation of each of these products. Now, I have not written out the complete mechanisms because they're in previous lecture, but also because you don't need me to. I have gone through this same mechanism about 6 times, so you just apply the steps. You would have proton transfer, you have heterolysis, and you can draw out the intermediates. And then that gets you to this carbocation. This carbocation where you have a strained ring adjacent to the secondary carbocation. It will rearrange. And it doesn't rearrange to make a more stable carbocation necessarily, because it's secondary in both cases. It rearranges to relieve the ring strain. Second example, we have same deal, same order of steps as before. Proton transfer, heterolysis, the loss of water, the good leaving group. And now we generate this secondary cation. And that secondary cation, it is adjacent to a quaternary carbon. So the smallest alkyl group will move, the methyl shifts, and you generate this tertiary carbocation, which is more stable than the secondary. And then, of course, that gets trapped by bromide in the coordination step. Last pattern. And again, we've already looked at these in the SN1 and E1 lecture. So if you need me to talk about it more slowly, I want you to go to that lecture. So we have a secondary secondary alpha carbon adjacent to a tertiary carbon. So in this case, we're going to see a hydride shift. So same order of steps. We would have proton transfer to make water, which is a good leaving group. We would have heterolysis, cleavage of this bond. So look like that. This bond cleaves. That generates the carbocation shown. It's secondary. Now it's adjacent to this tertiary carbon. The tertiary carbon has a hydride, a hydrogen, and that hydrogen is smaller than methyl, so it shifts over. So we have those sigma CH electrons donating into that empty p orbital on the alpha carbon, on the carbocation carbon, and that generates for us a more stable tertiary carbocation. Okay, your turn. What if now these alcohols were subjected to E1 conditions? So we looked at SN1 with rearrangement, What about E1 with rearrangement? Yeah, so I've just drawn the same cations that we talked about before. And now instead of some nucleophile X minus attacking the carbocation for coordination, we're going to have elimination. And we're going to have elimination to generate the more stable alkene. So even elimination will generate the most stable, so the most substituted alkene. When you have a choice, that's what you should do, because that's what nature does. So here there are two different beta hydrogens, two types of beta hydrogens. This one is eliminated to form this tri-substituted alkene. Elimination here would make a di-substituted one. Okay, same deal. For this carbocation that we looked at before, there's two beta hydrogens, two types of beta hydrogens. We eliminate the one to make the tetra-substituted alkene. If you eliminated here, you would only get a tri-substituted alkene. And draw that out if you're having a hard time following how fast I'm going. Just pause and draw the things out that I'm saying. And then finally, for the last example, we again have two types of beta hydrogens. And we'll eliminate at this one to generate the tetra-substituted. If we eliminated here, it would make a di-substituted, and that is less stable. So even elimination, it's going to generate the most substituted alkene, most stable alkene product. Take a moment and pause. I've asked you to do this slide before in the SN1 and E1 lecture. So write down, why do carbocation rearrangements occur, and what patterns are we looking for to predict when one might occur? Yes, everything occurs for the same reason, to make a lower energy, whatever, but in this case, to make a lower energy cation. The patterns that we're looking for, again, are strained ring adjacent to the cation. Quaternary carbon adjacent, let's write all this out. Quaternary carbon adjacent to a secondary cation. Tertiary carbon adjacent to a secondary cation. I think we see this pattern, right? Secondary cations, they're just less stable. And so they're more prone to rearrangement. So if you have a secondary cation adjacent to a quaternary carbon, you're going to have an alkyl shift. If you have a secondary cation adjacent to a tertiary carbon, you're going to have a hydride shift. And that hydride that moves ends up here. There was already one there. Okay, so that's the one that shifted. There was already one here. And then this last example, for some reason, I don't have too many examples of these types of rearrangements in the notes, but it's important to point out. You can imagine where you have a carbocation shift to go from secondary and just an isolated, localized carbocation to secondary with resonance. So if you have some sort of pi system, a few bonds away, or one bond away, adjacent to the carbocation, then you might have some sort of rearrangement to generate a carbocation that is delocalized or stabilized by the localization of charge. Okay, make sure you can recognize these four patterns. Super, we are done with the review. That took forever, right? So again, if you need to hear everything all over again, you go back to this lecture on SN1 and E1 reactions. I have a whole section on alcohols, and I have a whole section on carbocation rearrangements in that lecture. So re-listen to that if you need to. I want you to pause now and summarize what you have learned about alcohols as the starting materials, the reactants in substitution and elimination reactions.